Hello everyone, welcome back to lesson number 30 for BC Calculus. In this lesson we are talking all about volume. In the first two videos we talked about volume of a cross section, and the next couple of videos we're going to talk about volume with washers and discs. So I just want to reiterate really quickly that in order to find volume, all we have to do is integrate from A to B, which are going to be the bounds of our actual shaded region, which we'll talk about, and it can be in terms of X or Y, and we'll do examples of both. And then if you just integrate the area of what is being rotated, then you can get the volume. So let's go ahead and start this example by saying that find the volume of the solid of revolution. And so again, the key word here is volume of the solid revolution obtained by revolving the plane region R bounded by three functions. The square root of x, which is you guys see right here, the x-axis, which you see right here, and the line x equals 4. And so if we were to trace those three functions, we would have the shaded region right here. And so we want to rotate this around the x-axis. And this is actually really important. So what I always tell students to do is we're going to rotate this around the x-axis. And so what I end up doing here is we want to create a rectangle. We want to draw a rectangle that actually encompasses what our region is going to be. So if I go ahead and look at the rectangle that you guys see here, I want you guys to say, just really quickly, back to lesson number 29 for a second. If we want to find the area of this function, we would integrate this from 0 to 4, right? And because that's our left bound and our right bound. We've talked about this before. And then we would take our top function, which would be the square root of x, and we would subtract our bottom function, which would be minus 0 and then dx. So this right here would give us the area of this shaded region that we have right here. Well, again, back to our equation, well, volume is going to be equal to the integration from A to B of the area of our function. All right. So the first thing that I want to just say before we continue with this is that volume is going to be equal to, well, this is going to be the bounds as it is in lesson number 29. So our bounds are going to be where our left hand is of our shaded region and then where our right hand bound is. So we're still going to be bounding this from 0 to 4. Now, what I want to talk about with this particular example is that this, when we actually rotate it around the x-axis, then it's going to be a circle. So we have this region that's when we rotate around this, we're going to start seeing that's becoming a circle. So we want the area of this circle. So the area is going to be pi r squared. And so all we have to do is find what the radius is of our circle, and that's going to give us what we're going to actually integrate. Well, I'm going to go ahead and put the pi here because of the circle. The radius is going to be from the top of the curve to here, right? It's going to be the top of the curve to the actual bottom of the curve. Well, that's actually going to represent the height of our rectangle. Well, the height of our rectangle goes back to what we talked about in lesson number 29. The height of a rectangle is going to be the top curve minus the bottom curve, which is actually going to give us the square root of x. So our function that we're actually going to do, our radius is actually going to be the square root of x. And then we're going to square it, because again, this is going to be our radius. And then just like in the previous two videos, we also have to take into account the thickness of our of our circle, or the thickness in this case right here of our rectangle. So we have to also then multiply by dx. And so what we're going to always do, especially for these particular examples, is that we can always pull out of our constant, and so we're going to be left with the square root of x quantity squared. And I'm going to leave it the square root of x quantity squared because, just like in the previous examples, we had a function squared, right? We had a function squared. And so when we go ahead and plug this into, well, we actually don't necessarily need to plug this into our graphing calculator, but we could solve this by hand. But the video today is not about that. So if we do this by hand, we're going to get that this answer is going to be 8 pi. Okay? And again, it's all about that when we start rotating these things around these axes, it's going to create ourselves a circle. Now, I also want to say very quickly that if we're going to rotate around something that is a horizontal line, then our rectangle is going to be perpendicular to that. And so anytime you have a horizontal line, so this could be the x-axis, it could be the line y equals 1, y equals 2, y equals 3. Any horizontal line, you're going to do your function, you're going to write your integral in terms of delta x. So that's really important to understand. All right. Again, the other thing I want to say about volume in this particular example, when we're doing washer and disk, it's always going to be perpendicular to our axis. Okay, so I know that was a lot of babbling, but let's move on to the next one. So for question number 6, it says find the volume of the solid generated by revolution, again, by the curve y equals x cubed, the y-axis, and the line y equals 3. All right. So what I want to say about this one, and it's about the y-axis. So we're going to go ahead and we're going to revolve around the y-axis. Now, first of all, guys, the reason why the rectangle is drawn this way is if I were to draw the rectangle this way, then it's going to be parallel to the axis of rotation. And we will get into that in the very next lesson. So right now, all we're doing is we're learning how to do volume based on the fact that these rectangles we create is actually going to be perpendicular. So that's another thing that we're going to talk about, is that when we draw these rectangles, we want to be able to draw them perpendicular to our actual curve, or to our axis of rotation. And so we're going to draw them like this. So when we do this one, we're going to do volume, and as you guys can see before, we're going to create a circle, right? So it kind of, if you want me to continue drawing this function, it's going to draw like this. I'm a horrible drawer, but it's going to look like this. So we're going to rotate this thing around and around and around. It's going to become this beautiful circle that you guys see here. So first thing we're going to do is that if we're looking at the y-axis, so now we're going to look at something that's vertical. So these are vertical lines. Anytime that we're vertical, we're going to be in terms of y. And another easy way to think about that is the fact that up here, our rectangle distance, this width, is dx, right? We're changing our x values. Here, if we put our rectangle horizontally, this is actually changing y. So you guys can see that this little guy right here is changing y, and that's what you see right here. So that's just another easy way of thinking about those particular problems. So if we're going vertically, then remember, guys, again from lesson 29, that our bounds that we're actually integrating from is our low bound and our high bound, because all of this is all about y, like all of this was all about x. So this is going to end up being 0, and it actually tells us where we're stopping. We're bounded at y equals 3. So we're going to go ahead and bound from 0 to 3. And just like before, guys, we're actually going to find the area of a circle. Okay, the area of a circle. So, and this is why these are disc, right? These are why these are called disc, because they look like a disc. So, again, we have the pi. So the radius, and again, back to lesson 29 for a second, you're going to find this curve, right? It's always the right-hand curve minus the left-hand curve. But you have to remember that we can't use x cubed here, right? Everything's going to be in terms of y. So we actually have to solve for x, right? We want to figure out what this equation is. And so very tiny here, you guys can see that this actually ends up being x is equal to the cube root of y. So we want to rewrite this as x is equal to the cube root of y, just like this line right here, our left-hand curve, is actually x is equal to 0. So remember, up here, we want y equals. Here we want x equals. So just like before, our area is going to be the right-hand curve, which is going to be the cube root of y, minus our left-hand curve. So that's going to be the radius, that's going to be the distance of a particular rectangle, right? That's what this distance is right here. And so we have to square it because, again, it is it's the area of this circle. And then we're going to change y. And so we're going to go ahead and pull the pi out. And we're going to go 0 to 3. And we're going to go the cube root of y, and I'm going to keep it squared just like before, dy. So another thing that we can always talk about, guys, really quickly, is that if we actually have disc, you can always pull out you can always pull out a pi. And actually for a washer, you can also always pull out a pi. Now that's different from cross sections, because cross sections, remember, this number was different based on the shape that we talked about in the first two videos. Well, this is always a circle, so it's going to always be pi r squared. And so if you plug this into your graphing calculator, or you could actually also integrate this in by hand, but I do have the decimal answer for this particular problem, which is 11.763. Okay, so this is the video for disc. Washers, we're going to come into in the next video, where what happens if we don't revolve it beautifully on an axis. So I hope this makes sense. And one more thing I'm just going to say very quickly about this, because these are, again, are a disc, that when you are rotating around an axis or a line, it could be a line as well, there's no gap here. So you guys can see that if we take this line right here and we start rotating around this axis, we're going to always keep our cells not having a gap. So it's going to end up being this nice uniform circle. And that's a horrible, horrible circle that I'm seeing here. So I'm going to stop there for this video. And then in the next one, we're going to talk about what happens when we have a gap, which is going to end up being our washer. So I will see you guys in the next video.